Welcome back to Teaching Statistical Thinking. In our last video, we talked about the correlation coefficient. Remember, it was a measure of the linear association between two numeric variables. Also recall that it was unitless, falling between -1 and +1. Now from the correlation, it doesn't actually let us make predictions of y from x. So today we're going to be using the correlation coefficient, taking it one step further to help us draw a regression line that will enable us to predict our y from our x. So let's go. Recall from our last video, we were looking at a data set that was 9 points of 9 different movies, and we had plotted the audience rating for those movies versus their critic ratings. And the 9 points are here on the scatter plot. Also recall that the mean of y was 50 and standard deviation was 6. The mean of x was 70 and the standard deviation of x was 12. When we estimated our correlation, we got 0.54. We said on JMP we got it to be about 0.58. And so I'm going to round that and use 0.6 for our calculations today. So you ready to calculate the regression line? Let's do it. Recall that in the correlation coefficient, it was a measure of fit to a line. That particular line is the SD line. The SD line is a line that matches up the standardized values of x and y. So if a point, or if we're one standard deviation below on x, we're one standard deviation below the mean on y. If we're one standard deviation above the mean on x, we're one standard deviation above the mean on y. So the slope of the SD line, or the line for the correlation, is equal to the SD of y, the standard deviation of y, divided by the standard deviation of x. So if we increase by one standard deviation on x, we increase by one standard deviation of y. Now think about what that means. If each of our variables has a bell-shaped distribution, then if a point is 2 standard deviations above, it's at the 97.5th percentile. So if you're on that SD line, it means you scored at the same percentile on the x variable and the y variable. When we actually go to make predictions, we can do better than that line by flattening it a bit. And here's why. Look at values of x, where x is very low. Most of the area of the ellipse lies above that line. At the high end of x, most of the area in the ellipse lies below that SD line. So we're going to do better in our predictions if we actually flatten our prediction line from the SD line. How we're going to do that is our new slope for the regression line, instead of increasing by a whole standard deviation in y, we're going to increase by the correlation times the standard deviation of y for 1 unit in x. Okay. So our slope is going to be the correlation coefficient times the ratio of the standard deviations. Okay. The ratio of our standard deviations, the standard deviation of y was 6, of x was 12. So the slope of our SD line is 0.5. The slope of our regression is the correlation, which I've approximated at 0.6, times 6 over 12 is equal to 0.3. So now, as audience rating increases by 1 unit, the critic rating will increase by 0.3 units. For the regression line, it always falls through the point of averages. So we can use that to go after our intercept. We've got 50 is equal to 0.3 times 70 plus b. 21, so b has got to be equal to 29. So our regression line is the critic rating is equal to 0.3 times the audience rating plus 29. And that's our regression line. Now to draw that in, okay, I'm going to draw it in here. It's going to look something like this. Okay. It's going to be flatter than our SD line. And for 1 unit increase in x, y is going to increase by 0.3. Not so hard. Now, notice that none of our points fall on the regression line. Okay? So for each of these points, we have an error, which is called a residual. Here at 80, if we plug 80 into our regression line, 80 times 0.3 is 24, plus 29 is 53. So we would, for a point at 80 audience rating, we would predict their critic rating at 53. This point is actually at 80/60, so our residual is 7. Our average prediction error could be calculated by taking all of these distances from the regression line, squaring them, taking the average, and again taking the square root. That's called the root mean square error, and it's abbreviated RMSE. The root mean square error is our average prediction error. Now, fortunately, we have calculators and computers that can calculate that for us. But if we've got a lot of data points, we also can approximate it very easily. It's approximately the square root of 1 minus our correlation squared times the SD of y. Our correlation is about 0.6, squared is 0.36. 1 minus 0.36 is 0.64. The square root of that is 0.8 times the standard deviation of y is 6. So that comes out to 4.8. Our average prediction error is about 5. That concludes what I want you to know about regression. But before I leave you, I want to turn back to the Gates 2011 annual letter and look at the example that they presented us there. Remember back to the 2011 Gates letter and the image that we looked at in that letter. It was a scatter plot of IQ versus disease burden for 184 countries. Disease burden here is the life years lost from 28 different infectious diseases, and it's on the log scale. What I'd like to do today is take that scatter plot and let's just estimate what the regression line would be. So, to start, recall we need the point of averages, the standard deviations, and an estimate of our correlation. So looking at that scatter plot, the mean of disease burden is about 3.3, and the standard deviation is about 0.75. For IQ, on the y-axis, its average is about 85, and the standard deviation of y is about 10. Now you notice that the cloud of points has a nice strong downward trend. I would estimate that correlation to be about negative 0.8. So we know our regression line is going to have a negative slope. We want y equals mx plus b. Let's go after the slope first, our m. Recall, it's the correlation times the ratio of the standard deviation of y over the standard deviation of x. So that's going to be minus 0.8 times 10 over 0.75, which comes out to be negative 11. So as the disease burden increases by 1 unit, the IQ decreases by 11 units. Also recall that the point of averages falls on the regression line. So we know 85 is equal to minus 11 times 3.3 plus b. And solving for b, we get 121. So IQ of the country, recall this as 184 countries, is equal to minus 11 times their disease burden plus 121. And that's our regression line. That concludes the video on regression and concludes all the content for our principal videos. Next time we're going to return and do a review that covers all of the concepts that we've covered in the context of another example. So join us for our concluding video and then we'll wrap up. See you soon.